And welcome everybody. Hey, it's interesting in the world of networking how when an IP address has changed, things can change. And so I had OBS Studio set up where it was using a fixed IP address to stream from instead of the default address. And so my computer had been gone for a few days, got a new IP address for my DHCP server, and, and it wouldn't stream. All right, so anyways, great to have you. Thank you very much for joining me today for CCNA Sunday. We're going to focus today on a little thing called spanning tree protocol. I happen to really love spanning tree protocol. Let me tell you why. It's one of those things that it's important to understand how it works, but it can also save a person's bacon in a production environment if they're aware of why it behaves the way it does and what it does. So to start off, the word protocol, spanning tree protocol. A protocol is nothing more than a set of rules, of how something should operate. And if devices agree on those sets of rules, they can communicate and work with each other. So spanning tree protocol is simply a set of rules that layer 2 switches agree with and work with and participate in. And I have some basic objectives for our time together, and they are this. Number one, why would we have layer 2 loops in a network? I mean, what exactly is that? Why is it a problem? And so let's start there with the challenge of a layer 2 loop. And to do that, let me share with you, let's do this. Let's go to a computer. And let's go back to this PC right here, this client PC on this network. And this is in one of my labs. Let me go grab the client PC. All right, so this is the client PC. And if we bring up a command prompt, which I'll do right now, and we type in the command ARP space -A, that's going to show us the current ARP cache. That's the layer 2 addresses that this computer knows about other devices on the same local network. So at the moment, this device knows that to reach 10.16.0.30, and this is off our local interface 10.16.0.10, that if we wanted to forward a frame to 10.16.0.30, that we would encapsulate or use the layer 2 address of this bad boy right here before we sent those bits on the wire. So if you haven't yet seen our session on layer 2 switching and trunking, check that out. We'll talk all about the details of how layer 2 forwarding works. But the challenge here is that if we have redundant paths in our network or parallel paths in our network, there's the opportunity for, let's say we're going to throw something. Let's imagine we're going to throw this. We throw it into the network. If it just kept looping and looping and looping forever at near the speed of light, or however fast the network can forward it, that's going to be a waste of energy if it keeps looping endlessly. So I want to share with you a protocol analyzer right here. And a protocol analyzer is simply a way of looking at network traffic. I've got some captures right here. In fact, you know what? Let's just not look at one. Let's capture one. Let's imagine that we want to ping. Let's go back to our topology for a moment. Let's say we're right here. We're the client PC. And we want to ping 10.16.0.30, PC3 right here. So the traffic is going to have to go over these links. And I have a pen and I know how to use it. Let me get up my... not that. Let me get a pen so I can actually illustrate this and we can be on the same exact page. All right, right here. So these links right here in red represent trunks. And from our previous discussion, the trunk is simply a link between two devices that allows multiple VLANs to go over. So if we have VLAN 10 and 20 and 777 across the trunk links, we're going to add a little 802.1q tag, and so that the receiving switch can know what they are. So all the links here in red are trunk links. So let's imagine that Bob is sitting at this computer, and Bob types in ping space, and he pings the IP address of 10.16.0.30. Well, if Bob does not yet know the layer 2 address of this PC, he's going to do an ARP request. And that's what I'd like to go ahead and generate right now. I think it'll be fun to do. So we'll go back to our client PC, Bob's PC, and it is right here. And let's do an ARP. That's ARP space -D space asterisk. And that's going to remove everything from Bob's local ARP cache. So if we do an ARP -A again, he now no longer knows about 10.16.0.30. And before we try to reach that device, let's go ahead and do a capture. So we'll launch Wireshark. It's just a fun protocol analyzer. This is local on Bob's computer, and we'll capture all the traffic going in and out of this interface, and we'll minimize that, and then we'll just do a ping. So we'll do a ping to PC3, which is 10.16.0. I'm just going to check my diagram again. 10.16.0.30. Okay, same logical IP network, same VLAN, and let's go back to our lab, and we'll do 30. Press enter, And this first one took a little bit longer, 161 milliseconds, and that's very likely because it had to do the ARP first, and then the other three here proceeded. Well, that last one took a long time too. But ARP happened, so if we do a up arrow key a few times, ARP-A shows us that we now know the layer 2 address associated with PC3's IP address, and that was courtesy of ARP. So, because we captured that, let's go back to our protocol capture. We'll click on the little stop icon up here to stop the madness, and there's a lot of ARP traffic, but the one we're looking at is from 10.16.0.10. Wow, look at all that traffic. Okay, it's going to be before the pings. That's a good clue. So here we go, right there. Oh, Keith. Dang it. Hold on a second. I got a little bit too crazy with the mouse. Okay. Where is the ARP request? 10.16. I'm probably looking at it right here in front of me. Why I'm looking for the ARP. Unless it somehow ARPed before. It looks like the response. Maybe I cut some of that off. Okay, I'll tell you what. No problem. We're going to quit without saving. I fumbled figure something. So let's clear the ARP cache. ARP-D. Let's go ahead and verify it's not in the ARP cache. We'll start the capture. Make sure the capture is running first. And then we'll go ahead and we'll capture it. All right, so now that's capturing. Let's go back to our client PC, minimize this, and do the ping. I'm just using the up and down arrow keys. All right, so there's our ping. Let's go take a look at the protocol capture. This time I won't fumble finger it. All right, so here, right there, is our ARP request. So I'm going to highlight that. And if we look at the details of that, that is our PC at 10.16.0.10 with his source layer 2 address, sending out a message at layer 2. He's sending out a broadcast, all Fs, and saying, hey, anybody on the network, 10.16.0.30, if that's you, if that's your IP address, please respond back and let me know what your layer 2 address is. And then the next packet, we had that response. But what I like to focus on is this broadcast right here. A broadcast is, on a VLAN, on Ethernet, it's like shouting. And so we're simply shouting to everybody on that network. And let's take a look at what our topology would do with that if we didn't have something to protect us. And let's take a look at this topology right here. So here's Bob. Bob sent this broadcast into the network, and the switch received it, and the switch is going to forward it over these links. So currently these are trunk links. And so let's imagine that the broadcast gets forwarded this way. So switch 1 sends it, tags it, sends it to switch 2. Switch 2 sees it, says, oh, it's a broadcast for VLAN 10, forwards it to all ports associated with VLAN 10, including the trunk. So it goes down here. Switch 3 receives it, says, oh, that's a broadcast for VLAN 10, forwards it here. Switch 1 says, oh, hey, a broadcast for VLAN 10. I better forward that to all devices that need to see it, plus send over the trunks. And that would just continue looping unless we had something that identified that we had parallel paths. We had redundant paths, which we do here. So what happens without something like spanning tree to stop the parallel redundant paths from all forwarding? We would have packets that broadcast that would loop endlessly like this, clockwise, and also like this, counterclockwise, as they went over these links, and they just keep on going and going and going forever and ever. In fact, if we take a look at, in fact, we can do this right here. If we look at the client PC once again, and we just look at any one of these packets. So this is a ping reply. See at layer 3, for the IP information at layer 3 in the protocol stack, we have this really cool field, which is right here. It's called time to live. And here's how the time to live feels. This is not how it feels. This is how the time to live field works. If you and I are a router and we're getting a packet at layer 3, we're looking at it and saying, oh, I need to forward this, we're going to decrement the time to live every time we forward it. So get a packet, make a routing decision, decrement the time to live, forward it. The benefit of that little field in the layer 3 header is that if that time to live goes down to 0, routers are not going to forward it anymore. They're going to say, wow, this packet's time. Let's take a look at layer 2 and see what's at layer 2 that might help prevent a loop, like, for example, time to live. So here's the layer 2 information right here. Source layer 2 address, destination layer 2 address, and you'll notice there's nothing in that layer 2 header that says they're pulling, and they're amazing. A lot of work. The dogs, everybody's doing a lot of work. Well, there were some vacationers watching and there's a musher, and the sled dogs had just stopped cold. And the musher went up, got a stick, not a huge stick, but a little stick, and just whacked one of the dogs right in the back of the neck, and the dog went, "Whoa!" And then the dog got back in line because the two dogs had been fighting, and then the team started running again. And the onlooker, when they came at the finish line, they were doing photos and things, and the onlooker, the vacationer, said, "What's the secret?" And the musher, the driver, said, "You have to know which one to hit." Now, that's like spanning tree. Spanning tree is going to be sending these little messages across the network, layer 2 messages, and saying, hey, do we have parallel paths? And if we do, bonk. It has to hit links, meaning not tell them not to forward. They call it blocking. And that way those ports, even though they're present, they're connected from one switch to another. If they're redundant and they get chosen to not forward traffic, spanning tree is going to say, hey, I know you're willing to forward traffic, but don't. And that's the concept of spanning tree, identifying parallel paths and then specifying that we're not going to forward on certain paths. So that's what it does. Spanning tree identifies parallel paths in our network, and then it automatically not disables the ports, but stops the forwarding of traffic on those ports. So if we're looking at this topology right here, here's how we could solve this problem. We could just get rid of this link right here and get rid of this link right here. And then we wouldn't have redundant paths. We just have the path from switch 1 to 2 and switch 1 to switch 3. And if these links weren't here, these segments between the switches, if they weren't there, there would be no redundant. There would be no parallel paths. We wouldn't need spanning tree. Now, what's the negative side of only having one connection between switch 1 and switch 2 and one connection between switch 3 and switch 1? If you're saying, well, Keith, if we lose a link, if there's a problem in the network, we're going to lose service. And the answer, that is absolutely straight on. So we want to have the redundancy in place. However, we can't allow all the traffic to forward on all the links because there will be loops at layer 2 unless we use spanning tree. So on commercial switches like Cisco Catalyst switches, spanning tree is enabled by default. And it might be important to understand how the rules are played with spanning tree. And here's the basic rules. So our objectives for this session is to understand why layer 2 loops are a problem. And the answer to that is because there's no time to live function inside the header. And one broadcast could go on forever and ever and ever unless we identify that we have parallel paths and train the interfaces to not forward on one or more of those paths. Here's how STP spanning tree protocol operates. It's a collaborative effort. We take a group of switches and they're going to talk to each other. They're going to get chatty. And the way they get chatty is they send back and forth these little itty-bitty messages, and they're called, it's kind of a long term. It's a bridge protocol data unit. Bridge protocol. There's just these teeny little messages about every 2 seconds. Boom, here's the information. And these bridge protocol data units are how these switches can identify that there's parallel paths in the network. And so spanning tree, the way it works is it has an election, and they choose one. For every VLAN, there's going to be one root device, one King Kong of spanning tree. Now, they call this device a root bridge. And I thought to myself in the early days, why are they actually, in the early days when I learned it, we were using bridges. And that's why the term comes up. A long time ago, before high-speed switching came up, we had bridges, which act like 2 or more switch ports on our switches today, with layer 2 forwarding and all the rest, the same process. But now we have a separate switch port for every device on the network. So in the old days, when this was written, it was called spanning tree protocol, and we elected one root bridge. So when we think of the word root bridge, think of one switch that's going to act as the root bridge. If you want to call it a root switch, you can. No one's going to laugh at you. But technically, it's called the root bridge. So I've got a question for you. Imagine we have these three... Wait, let me back up. It's not going to take a lot of imagining. Check this out. If we have these 3 switches and we need to choose one of them to be the root, like the starting point for deciding how we're going to forward or not forward and decide that root bridge, the way they do it is they have something called a bridge ID. And a bridge ID is a number. It's quite a large number. But it's going to be unique for every switch. So switch 1 will have a bridge ID, switch 2 will have a different bridge ID, switch 3 will have a bridge ID. We can take a look at how that's created, and we will in a moment. But when I think of bridge IDs, I think of golf. And you might say, Keith, wait, what do you mean? You think of golf when you think of bridge ID? Yeah, I do. Almost every time. Because in golf, think about it. How does a person win at golf? The last time I swung a club, it was about 3 years ago in a simulator. So I'm not good at golf at all. But I knew the rules. I know who wins. It's the person with the what in golf? The lowest score. So if we have 3 switches and all of them have a unique bridge ID, the one that's going to win is like golf. It's the lowest one that wins. So what they do is when they're powered up, they start sending these little love messages, these bridge protocol data units to each other to communicate over those links. Hey, here's my bridge ID. Sort of like this. Let's see if I can actually make sure you can see these. It sounded like a really great idea when I put them together earlier today. Hold on one second. Let me go ahead and bring up this so I can verify. There we go. You got to know when to hold them. Know when to fold them. So basically, each switch has a bridge ID. They know what their bridge ID is, and they're going to use bridge protocol data units, these little BPDUs, send them across the links to the other devices, and basically everybody gets to read everybody else's card. So if switch 1 has one bridge ID, switch 2 has a different bridge ID, and switch 3 has a different bridge ID, which one's the lowest? I'll let you choose. And I'm looking at the cards in the monitor here. It's is this one right here. So the switch that has the lowest bridge ID gets to be the King Kong of spanning tree, meaning they call it the root bridge, the starting point, the core of the tree for spanning tree. That's how it's selected. So a couple things we've learned so far. Number 1, spanning tree is important because it has to identify if we have parallel paths, redundant links in our layer 2 network, which are a good idea in case we have a failure. Then secondly, amongst themselves, based on the lowest bridge ID that they've communicated with each other using BPDUs, they're going to choose one as the root bridge. And he wins. So basically, whoever has the lowest bridge ID is going to be the root for spanning tree for the entire spanning tree for that VLAN, for that network. All right. So that's the first step. Elect a root. Now, what happens next is quite interesting. I think in my mind that everybody wants to be the root. I want to be the root. I want to be the root. But only one switch is going to be the root switch. So everybody else, meaning all the other layer 2 switches, are going to fall in line. And they're going to say, okay, we agree. I mean, we can see, right? Your bridge ID is lower than mine. We learned them via BPDUs that were being sent. We agree. We're over it. And then they have to determine, okay, in this topology, which of my many ports, says the switch, which of my many ports is the most cost effective to get to the root switch? So let's go ahead and annotate this on the screen. So let's imagine that, and let me pick on this guy right here. Let's imagine that this switch right here became the root. Now this is also happening for all of our VLANs. And so for this discussion, let's play with VLAN 10, although the output is going to be very similar to VLAN 1 or VLAN 10 or VLAN 20 or VLAN 777 until we start tweaking things. But let's imagine we're taking a look at just the spanning tree for VLAN 10, and switch 3 is the root bridge. And, I just had it a moment ago, but remind me. Out of these 3 switches, how did they determine who was going to be the root? How did they know who was going to be the root bridge? So if somebody would just chat that in, or everybody chat that into the message board, just to confirm that we have that the switch that has the lowest, it's like golf, I remember that, the lowest bridge ID becomes the root. And once he's the root, everybody else agrees. They've seen the BPDUs. They condescend. They say, great, I understand, and you're the root. So the second step for those switches, and let's go ahead and let's call these guys loser 1 and loser 2. Now if these were people, that'd be so rude, but because they're switches, we'll be okay. So what does that mean they're a loser? That just means they're not the root bridge. So we're gonna have one root bridge and then everybody else who is not the root bridge. In fact, let me undo those. So the next step for these switches is to say, okay, great. What's the best way, or what's the most cost-effective way for me to get to the root? So switch 1 knows that switch 3 is the root, and it's going to go ahead and identify what's called a root port. Now here's the secret for a root port. A root port is on the losers. So on the loser switches, the switches that didn't become the root bridge themselves, each of them are going to have one and only one root port, and that's the best path that they're going to use to forward in the direction of the root. That's it. Now, the question is, how do they decide that? Well, here's how they decide it. More cards. To choose the root port, each switch is going to say, okay, I've got these BPDUs coming in on multiple interfaces, right? I know where the root is, and it's going to say, what is the least cost for me? Maybe this is switch 1 to get to the root. And it looks at its cards. It says, okay, the cost on one port is 4, the cost on another port is 2, the cost on another port is 6, and again, it's a lot like golf. So each switch, as it determines which port is going to be the one that I'm going to forward towards the root, it's going to go ahead and pick the one that has the lowest cost, and that port is going to be identified as what's called a root port. It's a port that's forwarding in the direction of the root switch. So it would look like this. So switch 1 would say, okay, and for this diagram, just I'm going to give you a heads up right now, these are all gigabit links, and the cost of gigabit links in spanning tree is 4, a cost of 4. So what would happen is switch 3, these BPDUs would be flowing out from switch 3, and switch 1 would receive those. And in those BPDUs, there'd be an advertisement that the cost is 0 because this is the root switch, and switch 1 would see on this interface gig 2/0 its cost is 4. So it adds up the cost on that interface plus the advertised cost from the root, and the total would be 4. So out this port, it would be a cost of 4, and for these other ports, it'd be a lot more. And let's talk about that. So switch 3 is the root, advertising a cost of 0. Switch 2 receives that, cost of 4. So now when switch 2 is advertising BPDUs down this way, it's also saying that the total cost from switch 2's perspective is a cost of 4, and switch 1 has a cost in this local interface of 4. So effectively, it'd be a cost of 8 on either of these links. So when switch 1 is identifying, okay, which port is the best one and only one I should use to forward towards the root, it's going to go for, like golf, the lowest cost, and that port in this topology, if this was the root, is going to be the root port. So switch 1 would show 2/0 as being a root port. That's it. I mean, that's how switch 1 would do it. And switch 2 would do the same thing. Switch 2 would say, okay, great. What's the cost to get to switch 3, who's the root? And in this topology, this would be a cost of 4, advertised cost of 0, plus the cost of 4 on the local interface. So this would be the root port, and it would make its forwarding decisions, and this would be a forwarding port in the direction of the root. So here's the key. For the losers, I'm going to put that up here again. For the loser switches, they are going to have one root port, which is the port that is their best option if they choose to forward traffic in the direction or towards the root bridge. So each switch gets one root port apiece as a forwarding option. So also, this is also called a role. So if you ever see the concept of a root port, realize that's the role of that port, and root ports are also in a status of forwarding. So a lot of times what happens with spanning tree is there's a few terms involved. And so when people start talking about forwarding port, root port, I just want to clear up that the actual role of this port is called a RP, a root port, and root ports by default are always forwarding in the direction of the root bridge. So a root port, so to summarize, root ports are always forwarding in the direction of the root bridge. That's it. All right. So let's talk about, let's talk about one other direction. In fact, I'd like to ask you, and then we'll talk about it together. If we have two options about forwarding traffic, and if we're not the root switch, or even if we are, we have two options regarding forwarding. One is towards the root bridge, and that's what we just described. So if we have ports that are forwarding, and we have one each per switch that's forwarding towards the root bridge, that's referred to as the role of a root port. There's also an option to forward away. What do you mean away? Well, if we have a port on a switch that's forwarding away from the root switch, it would look like this. Let me put a different color on here. Let me go ahead and use blue. That'll work. Oh, changed my mind. Let me use whatever color that is. All right. So if we have a switch 2, for example, it's forwarding, and it's forwarding on this port or this port. In fact, let me go to black so it's easier to see. If it's forwarding here, that would be an example of forwarding in an opposite direction or away from the root. So the root port would be forwarding towards the root, and the ports that are forwarding away from the root in the opposite direction would be considered forwarding away. Those also have a role, and that role is called a designated port. And it's always forwarding, by the way. So if you have a designated port, it means two things. It means it's forwarding away from the root switch, and it's also forwarding. Two things in the same sentence, actually. All right, so let's take a breath. A couple basic things. Number one, if we have loops at layer 2 that don't go unchecked, we're going to have broadcast storms that just loop and loop and loop and loop forever at layer 2, which is a problem. So spanning tree steps in, and it's on by default on commercial switches, including catalyst switches. And spanning tree says, great, we're going to go ahead, if it's running, if the service is running, the spanning tree protocol, it's going to elect a root bridge. And it does that based on the lowest bridge ID. So whatever switch, by advertising the BPDUs across the network, if whoever has the lowest bridge ID becomes the root. Then the other switches who are not the root identify their root ports, the best path to get to the root. And then any ports that are forwarding away from the root, those are referred to as designated ports. So far, we haven't talked about any type of blocking whatsoever. We've talked about identifying a root switch, we've identified root ports, and also designated ports. But we do need to bring in blocking into play, so let's go ahead and do that right now. And let me clean up the screen just a little bit. There we go. All right, so let's go ahead and imagine, let's take it from the top. Let's say Bob is right here. And Bob is going to ping this device. He sends an ARP request as part of that ping, and we don't want to have a layer 2 loop forever and ever here. So spanning tree beforehand figured out the topology. Switch 3 becomes the root bridge if it has the lowest bridge ID. And we have two roles we've talked about so far. We have ports that are designated. And designated means this: we're forwarding traffic, forwarding frames away, or in the opposite direction of the root bridge. All right, and then so on this switch, the root switch, because it is the root, it has the opportunity of having all designated ports. So if this had 20 ports, they would all be designated, because let's think about the definition. It's forwarding away from the root. It is the root, so everything leaving it is forwarding away from the root. So all of its ports would be designated. And then regarding root ports on all the other switches, that is in a state of forwarding towards the root. So in this case, switch 1 would calculate that this is the best path based on the BPDs that are being shared. So this would be the root port. And then switch 2 would identify that this is the best path. It would be shown as the root port. And then the tricky part comes in up here. Now, on these segments right here, if somebody's got to, let's talk about the reality here. Somebody's got to block traffic. Otherwise, we're going to have a loop. And so every switch is going to have one root port, and every segment, which is, let's say, it's like every connection between two switches, is going to have one designated port, somebody who's forwarding for that segment. And that means if you've got these two switches, switch 1, switch 2, and they both are connected, on one side, we're going to have some designated ports that are forwarding away from the switch. And on the other side, we have to have some blocking going on. So let's take a close look at how that happens. So we've talked about the root election, which is based on cost. Oh, excuse me. I'm ahead of myself. The root bridge, which is based on low bridge ID. Great. And then for the other devices, they then calculate their root ports. So this would be A, elect the root. And then on the non-root switches, they identify their root ports. And then for C, then we need to go ahead and calculate the designated ports for everything else. DEZIGNATED ports. So these are going towards the root, these are going away from the root. So on the root switch itself, all ports are designated, meaning they're all forwarding, and they're all forwarding away from this device, the root bridge. So then here on switch 1 and switch 2, the question comes in, okay, who gets to be designated? Is it going to be switch 1 or is it going to be switch 2? And to ferret that out, the one that gets to be designated is going to be the one with the best cost. So what happens is there's going to be BPDUs that go between switch 1 and switch 2. And in those BPDUs, switch 1's going to say, hey, my cost to get to the root is 4. Beat that. And switch 2 is going to say, my cost to get to the root switch is 4. Beat that. And you might see that we have a tiebreak. We have a problem here because both switches have the same cost. So what do you do next? Well, if the cost is the same in this scenario, the next tiebreaker is the lower bridge ID of the two. So neither one of them won the spanning tree root bridge election, but between them, switch 1 and switch 2, the one that has the lowest bridge ID in this scenario is the next thing to look at as a tiebreaker. So let's imagine that this guy has the lowest bridge ID, and let's imagine that this guy is in second place with the second best BID. I'll put bridge ID there. And this guy is the third, as far as the third best bridge ID. What happens is, as far as who gets to be designated for these two segments, if the cost is equal to get to the root, this switch number 2 is going to say, oh, I win because I have a lower bridge ID than you do, all other things being equal. And that would make this port designated, this port designated. And then what would happen is you're only going to have one designated port per segment. And as a result, switch 1's going to say, oh crap, that means I lost. And it's true. So these two ports would go into what's called blocking state. BLK for blocking, because that's parallel paths, redundant paths. So neither of these two interfaces from switch 1's perspective would be used for forwarding traffic. And our spanning tree topology would effectively be the link between switch 1 and switch 3, between switch 3 and switch 2, and then the two links from switch 2 over to switch 1, they would be forwarding, but switch 1 would never forward in this direction. It would never forward out 1/2 and 0/0 because it lost the spanning tree process. So before I show you that, which I'd like to right now, let's confirm a couple basics about spanning tree. We need it because layer 2 loops are going to devastate our network. We want the redundancy in case anything changes, but we don't want to have loops. So spanning tree running by default elects a root bridge based on the lowest bridge ID. It does that by sending bridge protocol data units. The one with the lowest bridge ID wins. And then once that bridge ID that spanning tree root bridge has been identified, then the other switches say, okay, great, I need to calculate my root port. And that root port is going to be based on cost. So if a switch has a cost of 2 and a cost of 4 to get towards the root or forward towards the root, it's going to say, I'll choose the one that has the lowest cost. It would choose that. That's going to be the root port. Then every segment for forwarding away from the root needs to have a designated port, a forwarding port that's going away from the root. And you can't have two designated ports on the same segment because that would cause that's an implication of a loop in the network. So to battle that out, if there's two switches, they're both connected to the same network, they're going to battle out and say which one has the lowest cost. Hey, my bridge ID is 2. If the cost is the same, we both have the same cost, they'll then go to the bridge ID to battle it out, and then the one with the lowest bridge ID is going to win. And that's how that operates. All right, so I think we should take a look at this in a lab environment. All right, so I've got these ports all set up, and let me clear off that screen, and let me bring up this. Oh, there's our capture from earlier. Fantastic. I'm going to say quit without saving. All right, and let's log in and go to some consoles. So let's go to switch 1 first. So the way we could verify what spanning tree is doing, what it's looking at, and how it's performing is do the command show spanning tree. And then if you just press enter, it's going to show you all the spanning trees for each and every VLAN. If you want to focus just on one, as I do here, just tag in the VLAN identifier, and it'll show us the spanning tree for spanning tree instance for VLAN 10 don't exist. Wow, that's so curious. This is switch 1. I thought it was switch 1. Okay, VLAN 1's there. That's good. That's a good sign. And let's add 10. So it's got spanning tree. What's going on with switch 1? Well, let's make sure the VLANs exist. Okay, so VLAN's there. Show spanning tree. Spanning tree's running for VLAN 1. And there's VLAN 10. What did I do? What did I do? Show history. What did I do? Show spanning tree for VLAN 10. How come that didn't show up? Oh, I put show spanning tree 10. Yeah, I thought the word VLAN, just didn't say it. Okay, show spanning tree VLAN 10. So we got a little extra troubleshooting there. All right, so there's spanning tree for VLAN 10. And here's what is happening with this output. With this output, there's 2 sections. The first part is identifying for VLAN 10 who the root is, who King Kong is, who won. And that's all about this top part right here. So the bridge ID is made up of basically 3 components: the priority plus the VLAN number. There's a bigger story behind that, but we can cover that a different day. Plus the base MAC address. So those elements are right here. Here's the priority, there's the base MAC address, and also we're adding into that the VLAN. So for 32.768 plus 10 more for the VLAN ID plus this MAC address, that makes up this bridge ID. And the lower is better. So what this is saying is that the root switch is this guy right here. And my cost to get to him, says switch 1, is a cost of 4. And my root port is gigabit 2/0 to get to that I'm forwarding on to get to that root bridge. And it also is shown down here as well. So if we look here, it says to get to the root it's gig 2/0. Here's gig 2/0. Its role is the root port on this non-root switch, and its status is forwarding. And the cost is 4. And then it has a priority identifier as well, and that's its root port. Now down below here, the second part, which I'll put in a different color, right here, this is the information about switch 1 itself. So this is the root bridge above here. And this is, I'm going to say self. When we say self, I'm talking about switch 1. So switch 1 says, okay, this is my priority, and this is my address, my base MAC address, which makes it my bridge identifier. If you'll notice, the reason that this switch did not win for VLAN 10 and become the root is because it had something worse than the root. So the priority was the same, 32,007. What's showing up here as the priority is showing up as the same for both of them. But if you look at the base MAC address, it's 0064. That's the same. 3472. This is 34FB. So that 7 on the root bridge is lower, like golf, than the F here in hexadecimal, which is decimal 15, which is higher. And that's the reason that switch 1 did not win the root bridge election, because it has a worse or a higher bridge identifier. And then it's showing us the status of all the ports here. So the key thing I want to focus on here is the concept of designated ports and root ports. Root ports are forwarding in the direction of the root switch, and there's only one root port per switch. And designated ports are forwarding away from the switch. And there might be more than 1 or 2 or 3 or 4 designated ports. because you may have one or two or three or four more ports on that switch that are forwarding away. So Bob, the client, if I look at my topology real quick here, Bob, the client, is off of gig 0/1 in VLAN 10. And so because this switch 1, is forwarding on that port for VLAN 10, which is what that port is assigned to, that's why this is a designated port. And then the other ports here are in a blocking state. And that's where Spanning Tree is stepping in to protect the network. Boy, there's like I may take a second session and talk about some additional details for Spanning Tree, but I wanted to make sure that we got some basic concepts. And let's take a look at switch 2. So this is switch 2. Show Spanning Tree for VLAN 10. So switch 2, it says, hey, the root is this bad boy right here. I'm not it. So the second element here is switch 2's information. He also lost Spanning Tree Election for VLAN 10. And from switch 2's perspective, the port that's the most optimal to forward towards the root is gig 2/2. If we take a look at our topology, that's this interface right here, 2/2. And it is the designated port. Oh, look at this. Let's take a look at topology one more time. So on port 1/3 and 3/0, it's the designated ports for those two segments. So it's forwarding on 1/3 and 3/0. And so when switch 1 and switch 2 are duking it out on who gets to be the designated port, meaning who for those segments is going to be forwarding away from the root, switch 2 won. And it's probably, in fact, I'm sure it is, because they both have the same cost to get to the root. Switch 2 must have a lower bridge ID. And we can verify that very easily. So let's take, so here's switch 2. And if we take a look at the bridge ID for switch 2, it's right here. So I'm going to just swap back and forth between these two. There's switch 2, here's switch 1. I'll highlight those as well. And because switch 2 won, yeah, 34 AF right here for the base MAC address portion of the bridge ID, that is lower, 34 AF is lower than 34 FB. So A is numerically lower number than F, and that's why it won. So there we have an example of Spanning Tree at work protecting this network, and the blocking is all happening here on switch 1. So if we were to draw out this topology, which I think we ought to do, let me go ahead and bring out a pen again. We have the root switch, aka the root bridge. All of the ports on the root bridge are going to be designated forwarding away from the root, because it is the root. That's one of the wonderful things about being king. You get to do everything, and the root's going to be designated ports for all segments it's connected to. Switch 1 is going to have the best cost to get to that root off of port 2/0, so that'd be the root port. Switch 2 has its best cost to get to the root off of its 2/2, so that'd be a root port. And then up here, because the client's in VLAN 10, that'd be a designated port. And if this trunk is allowing that VLAN, that's also going to be a designated port, depending on whether or not it's allowed there. And then for switch 1 and switch 2, they duke it out. They send their BPDUs back and forth. And as they do that, and they say, okay, who gets to be designated for these two segments? Switch 1 and 2, they both say we're both a cost of 4. In fact, let's just verify that real quick. Are they both really a cost of 4? So switch 1 says my cost is 4 right there. And switch 2 says my cost is 4. So then came down to the bridge identifier between the two, so they could duke it out and battle for who's going to be designated for those two segments. So each segment, each connection between switches is going to have only one designated port per segment. And switch 1 over here lost, and so it's going to be blocking on both of its ports there. Okay, so let's take a look at a review, and then I've got one additional snafu that I'd like to share with you. So the pecking order in this, we start with 3 switches, but the pecking order is this: the switches all send BPDUs out. They share their cards with everybody else, and the one that has the lowest bridge ID is going to be the root bridge. All of its ports, all of the root bridge's ports are forwarding and they're going to be forwarding away from the root. And so what do you call a port that's forwarding away from the root? That is a designated port. The other switches who didn't win the election to be the root bridge are going to have to calculate based on the BPDUs they're saying, and they're going to have to calculate based on the cost to the root, which is the best path. And each switch that's not the root is going to choose one port, and it's going to be the root port that they're going to be forwarding on in the direction of the root. Then, after that's all decided, for forwarding away from the root on the non-root switches like switch 1 and switch 2, they're going to, who gets to be designated? Who gets to be forwarding on these links that are forwarding away from the root switch if there's more than one switch out there? And the answer is the one with the best cost. And so switch 1 and switch 2, if one of them has a better cost to get to the root, it wins. I'm forwarding. Cost is king. However, if the cost is the same, then they duke it out and they say, well, let's go ahead and handle this like gentlemen or ladies or whatever sex they are. And what we'll do is we'll simply allow the person who has the lowest bridge ID between switch 1 and switch 2, between those two, to go ahead and be the designated ports and to do forwarding. And at that point, the one with the lowest bridge ID is forwarding and has designated ports, and the other two ports on the other switch in this topology say, yep, you got it. I'll be blocking here. That's it. Now, there is one other scenario that is worth mentioning that I think a lot of people get wrong. And so I want to give you a heads up on it that so you don't get it wrong. And it goes like this. Let me clear off the screen. And it goes something like this. What if switch 2 is the root? So it's the root bridge. And so we're advertising BPDUs from the root. So these ports will be designated ports, designated ports, designated ports. Everything is forwarding away from the root is a designated port, and the root bridge gets to forward on all of its ports. So great, those are all designated. And so switch 1 is hearing these BPDUs basically on this link and saying, hey, the cost is 0, because the root bridge is the root, and the BPDUs. And it says, hey, the cost is 0 on this link. And it knows that its local cost is 4 for each of those gigabit interfaces. Now it's got a problem, because switches, you can't have more than one root port. So switch 1 says, oh my gosh, I can only have one root port. They're both the same cost. And check this out. Switch 2 in those BPDUs is advertising the bridge ID. So effectively, I think I have a card for this. I do. Let me bring up a card. Here it is. So let's imagine we get BPDUs coming from the root. So switch 1 sees it, and it sees the root bridge ID, and it's the same. So because it's the root switch on both its ports sending out these BPDUs, the root switch bridge ID isn't changing. It's the same on both. So here we have the problem with poor switch 1 saying, oh my gosh, problem. I'm not the root. I get that. I want to identify my root port, the best cost to get to the root, but I'm getting these BPDUs, and they're both the same cost to get on either interface, and they're both coming from the same bridge ID. So I can't use that as a tiebreaker because the bridge ID is the same. What do I do? And this is the part I think that probably, if I took 100 CCNAs, if we took 100 CCNAs, we'd probably have to give them back at some point. But if we took 100 CCNAs and asked them this question, they would probably get it wrong. But you're not going to. Here's the tiebreaker. Let's go back to our topology. When these BPDs are coming in, and switch 1 is trying to decide which of these two ports, 1/2 or 0, 0 is going to be the root port, the way it decides is it looks at those BPDUs from each of them, and it uses this information right there. The sender's port number, not my port number. Switch 1, you go away. It's the sender's port number. That information is included as part of the BPDUs, and it's like golf. It's like golf. So in the BPDUs that switch 1 is receiving, the sender's lowest port ID in the BPDUs, in this case 4 is lower than 6, it would go ahead and use that, and it would make that port where it got that lowest sender's port ID as its root port. So that's a tiebreaker. Again, most people get, I shouldn't say most, but I bet probably more than 50. Get that wrong. It's not my local port number, says switch 1. It's the advertised port numbers. In fact, I think we have time. Let's do a quick verification, and we'll show you that in action so you can see it. So let's go back to our screen real quick. And at the moment, switch 2 is not the root, so let's fix that. And I'm going to have another session on spanning tree because there's a couple other really good pieces I want to share with you as well. But in the basics of spanning tree, which we're doing now, let's go back to our command line interface, and let's go to switch 2. And I'm going to make switch 2 the King Kong. So config T, spanning tree, VLAN 10, root primary. So what this does is this command simply says, hey, I know what's going on with spanning tree. I've seen who the root is. I know what the priority is of the root. This command has one mission. Here's the commander's intent. Win! What do you mean win? You take whatever that priority is and you go lower. And that's what it does. So this command simply tells switch 2, win. And we'll do it right now. So we'll go ahead and press enter. Spanning tree doesn't take too long to go ahead and reconverge. And as it's considering life, if we do a show spanning tree for VLAN 10 now, check it out. So for VLAN 10 is on switch 2. It's saying, this bridge is the root. I just won because I artificially lowered my priority based on that command you told me to. I went lower than the winner, and that made me the new winner. So it's now the winner. So it's advertising in BPDUs that that's the root. And it's also advertising its own information. And because it's the root, this is going to be the same information. And you'll notice now it's forwarding on all ports. So if we go back to our topology, which will be fun to do. Let's do that right now. Here in our topology, let's do this. So this is the root. It won because it has the lowest bridge ID. I'll say root bridge. And just to be clear, it's not a root port. Bridge. Great. So these ports are designated ports. And if port 1/0 is in VLAN 10, it'll be a designated port. If port 1/1 is in a different VLAN, it won't apply for this instance of spanning tree. So the root bridge is, he won. He's the lowest bridge ID. All of his ports are forwarding away from himself. So designated port means forwarding and away. Designated means forwarding and away. And then as switch 1 receives those BPDUs with that information, it says, oh no, they're both the same cost. They're both coming from the exact same bridge ID. It will then choose the advertised lowest port number, which would be 1/3 in this topology. And that would mean it would choose 1/2 on its side, because that's where it heard that bridge ID, or that BPDU with the lower port identifier. And that would be the root port. And it would go ahead and block here, because it would be a loop if it didn't block. All right, advertisers, bridge ID. Our advertisers, the port identifier. So, you know what we ought to do? Let's test that. I think we should test it. Let me clear off that screen, and let's go verify that that is indeed our results. So here on switch 2, it's forwarding. It's the root. All the ports are in the role of designated. That's right here. Great. The status is forwarding, and if we take a look at switch 1. And do a show spanning tree for VLAN 10. We are expecting. There we go. There's our root port. You know what? I gotta be honest. I was like, that's what it should do. I hope it does that. But that's the result. So gig 1/2 is the root port, and it is forwarding because that's what root ports do. They don't block. Root ports are forwarding towards the root, and designated ports are forwarding away from the root. So in this topology, gig 0/1, which is where Bob's computer is connected as an access port, is also a designated port. And then it's blocking on gig 2/0, which is the connection down to switch 3. And it's also blocking on 0/0, which is that second port in our topology between switch 1 and switch 2. Yeah. I was just thinking there's probably a few more things I could. Oh, just one more thing. Let me let me show you what this looks like if we look at trunks, because we covered trunking and switching in another session. But if we do a show interfaces trunk, And that very bottom section says VLANs allowed on trunk and being forwarded by spanning tree. Any ports here that we have that are blocking for spanning tree will not show as forwarding. And so that's another way from the show interface trunk command you can see what's going on with spanning tree. So let's take a look at that. So here on switch 1, and just to confirm our topology here, this is blocking, is said. Let me just confirm that. And so many buttons, so many buttons. Yep. So gig 2/0 is currently blocking. Great. So we go back to our topology here. That's blocking. So if we do a show interface trunk, even though we have a trunk here between switch 1 and switch 3, it is not going to show VLAN 10 as being forwarded over that trunk link because spanning tree says no, that's blocking by spanning tree. So let's verify that. So show interfaces trunk. There we go. So gig 00, none. Gig 1, gig 1/2, which is the link between switch 1 and switch 2, is forwarding for VLAN 10, and then gig 2/0 is the forwarding for the other VLANs, and that's because we only made switch 2 the root for VLAN 10. I didn't tweak it for these other 3 VLANs, so that's why it's forwarding for VLAN 10 on trunk on port 1/2. All right, that's a lot of fun. Let's summarize, and then we'll close it off. Here's what we've learned about spanning tree. Spanning tree is needed because if we had layer 2 loops, we'd have one broadcast that would just loop and loop and loop because that layer 2 in the header, there's no time to live, there's no expiration of those frames. They would just loop and loop forever if they were allowed to. So spanning tree comes to the rescue. Spanning tree jumps in and says, okay, we need one sheriff in town. And the way we identify that sheriff is we share our cards with each other. And the way we share cards in spanning tree is with BPDUs, Bridge Protocol Data Units, that include the bridge IDs. And the lowest wins. So whoever has the lowest wins. And originally in our topology, it was switch 3, 1 for everything. So now switch 3 is the root. Now what everybody else does, it says, okay, I'm not the root, but I need to identify the best path to get to the root. And we do that by identifying the cost. So here we go. So if I'm a switch and I'm identifying my single root port, I'm going to go ahead and I'm going to identify based on the cheapest way to get there. If one interface is a cost of 6 and the other is a cost of 2, that's going to be my root port. I label that as the role, root port, and I'm always forwarding on that root port. That's what root ports do. And for going away from the root, we have designated ports. So on the root switch, all ports are designated ports, meaning we're all forwarding away from the root. And each network segment, each connection between switches is going to have one designated port. So if there's a conflict, if you get 2 switches, they're both connected, and they're both forwarding on those ports away from the root, they're going to have a little duel. And the duel goes something like this. What's your cost to get to the root? And if it's the same, if it's lower, that one wins. If they're the same, then they go to bridge ID. And then the lower bridge ID wins. And in a situation that we just looked at, if you have a non-root switch and it's receiving on multiple links the same cost, the same bridge ID, the tiebreaker then becomes the lowest advertised port. And I just grabbed some screenshots also I want to share with you, and then we'll close this up. So this is an example of before we changed the spanning tree topology, going from switch 3 to switch 1. And in this spanning tree protocol information, it included, let me change my color here, it included the root identifier, which is a combination of the priority and the VLAN and the base MAC address. By the way you can see the base MAC address is you can either do a show spanning tree, that'll work, and then the base MAC address shows up, or you can also do a show version, and show version will also show you the base MAC address. And because all the MAC addresses are going to be unique, in theory you'll never have 2 identical bridge identifiers. So in this BPDU it was sending, it had the root identifier, it also had its own identifier, and because in this example it was the root, so this is coming from switch 3 going to switch 1 when it was the root and its own ID are the same, and then it also includes this port identifier right here. So that could be a tiebreaker if we have multiple links where the bridge ID is the same, the cost is the same, and we have to go down to the port. That's the advertised port literally right there that the receiving switch would go ahead and use to make a decision. All right, one more. And this is from switch 2 to switch 1. This is before we made switch 2 the root. And so here in this topology, switch 2 is sending a BPDU. That's what this is. And it's saying, hey, this is the root, which was switch 4. I'm sorry, switch 3 was the root, cost of 4. And then it also down here, also in the bridge protocol identifier, it identified itself. So the message said, this is the root, this is me, says switch 2, and here's my port identifier. Let me clear that off. Right here. So in the event, in fact, this is switch 2, 3/0 going to switch 1, 1/2. If we look at the next frame here, which I also captured for us, notice that the port identifier is different. And so here it's hexadecimal 8008, and on the previous one, if we look at that, it was 800D. And so 8, the last character there, is lower numerically than D, and that's what, and that was the lower port number, equating to the lower port number, and that's why switch 1 chose the root port it did. So I just wanted to just kind of give you a reinforcement that the tiebreaker, the first one is lowest bridge ID first. That wins the root, the root bridge. And then all the other switches based on cost, choose the lowest cost to get to the root. And then after cost is neutral or even, then it's bridge ID. And if the bridge ID is the same, then it goes down to advertised port ID, which is then going to be used to choose the lowest advertised port ID is going to be the root port on that downstream switch. All right. You know, I didn't think it was going to take that long. Oh, we're going to talk about spanning tree. There's a few other things I'd like to chat with you about, including rapid spanning tree, and also I think this also ties well into some ether channel. So I will build those all up coming up in future sessions. So I'm also building a playlist. Super excited about that. The playlist is going to have, I'm just going to collect all these pieces that I've done and put them in a playlist for CCNA studies. And I'm also starting up on Saturday. Subnetting Saturdays, and so we'll do those live as well, and then we'll collect those and put them in a playlist so that somebody who wants to, just on YouTube, get a good starting point into a lot of the basics of how networks operate and Cisco CCNA, they'll have a place to go where they can get a lot of that information and have it in a nice organized fashion. So if you haven't subscribed yet, please do so. Certainly super glad about you participating and showing up here with me in these live streams. It means a lot. And let me take a look at my, so Saturday is going to be, what day is it? Oh, wait, let me back up. New Year's Day is Wednesday. We're going to take a look at OSPF network types. And then going forward on Saturday, we're going to start subnetting Saturday, starting off with the basics, how it works. I use my finger techniques, which has been very popular for people who don't like the power of 0, which if you're not a math person, it's not always straightforward. So I'll teach you those parts on subnetting Saturday, and then we'll continue on with some more spanning tree and also some ether channel, and then we'll work our way to layer 3 routing, and it'll be a hoot. So thank you everybody for joining me, and we'll see you in the very next session. Stay tuned to social, and I'll post all that information when it's coming out. In the meantime, thanks again, and happy studies and a happy brand new year. Thanks everybody.